Welcome to the session. Greeting of the day. In today's class, we are going to talk about the various properties of the penetrant available. We have seen some few very known factors, that is, it should be porous and flammability, it should be there above 95. So such one or two points we have seen already. Few more points are there out of nearly 9 to 10 properties it should penetrant should have. That we are going to see now. This point we have already discussed in previous content of capillary actions, a capillary force. In between the two samples, the surface of these two has some force. That maybe we are naming as surface tension of the liquid, surface tension of the surface, which absorbs the liquid inside. So this action is called as capillary action. So it is one of the properties. So we are going to see about capillarity, surface energy, viscosity, specific gravity, water washable penetrant, thermal stability, volatility, fluorescent dye thermal stability. So here we have discussed water washable penetrant, thermal stability, fluorescent dye penetrant, thermal stability. I have divided the flow chart itself. You could have seen based upon the physical. One is visible penetrant, one is a fluorescent penetrant. So here also property also it comes in the two ways: water washable penetrant, thermal stability, fluorescent dye thermal stability. So next we have flash point. We know that it should be greater than 95, and then removability to be easy and non-toxic to be odorless. So those things we will see one by one. Number one, I have taken as a capillarity. It is the ability of a liquid to flow in a narrow space without the assistance of an external force. We are not giving any external force, but those surfaces having the force, some surface energy. Those surface energy which interacts, those molecules interact with the liquid molecules to attract. That happens, that process I am calling this as a capillary action. This property helps the penetrant to fill the void. Where is void? This is the void, and liquid is filled here and it comes down onto the void by capillary action. When we are using the menses and dipping into the liquid, due to the capillarity rise, the menses will fill. The liquid is going inside the menses itself. So this is known as a capillary testing. So we are keeping the a bath and a tube through which automatically the liquid rises here. So this is called as a capillary action. Second one, surface energy or wetting capability. Important characteristics of the liquid penetrant material is its ability to freely wet the surface. This property we have discussed that the contact angle based upon the surface tension of the vapor to liquid to vapor conditions, surface tension of surface to liquid, surface tension of solid to vapor. So based upon these three, contact angle is generated. Here I can able to in the same image you can write here we have a surface tension of liquid to vapor. Here we have surface tension of solid to vapor. Here we have surface tension of liquid to solid. So these three makes some movement of this liquid. When the degree angle theta is greater than 90, it will be non-wettable conditions. Larger the angle, poorer the wetting, non-wetting, not wet. But the smaller the angle, it means less than 90. Theta is less than 90. We can tell it's a good wetting. It's a good wetting. It is non-wetting which is greater than 90, and if it is less than 90 degree, it is wetting ability is there. So likewise, based upon the surface tensions of those energies. The contact angle is the angle formed by remaining. The solid liquid interface, I am talking about this is solid liquid interface. Solid, this is solid. This is liquid. Solid liquid interface, and also about the liquid vapor interface. Where is liquid? We have a liquid here and subjected to vapor outside the nature. A liquid vapor interface. So this angle, see, with respect to this angle, the theta is formed. One is contacting with the liquid and solid, one is contacting with the liquid and the other side we have an open environment. With respect to this, we are identifying the wetting surfaces and contact angles. Liquid is wet surface when the contact angle is less than 90. That's what I have drawn in the previous one. For a penetrant material to be effective, a contact angle should be smaller. If it is smaller, what happens? It can able to flow easily, not denser. See, this is very large and it is sticking over at one location. But see, it is spreading over there. It having some good fluidity when it can able to spread over the surface and it can able to float into the crack also. But it does not matter. So here, when we have a crack here, due to its large contact angle, it is not possible to move. As it is not possible to move, it cannot able to penetrate here also. It means the crack is missing. It is not visible, or error is not determined. As we have not at all went there, then how to determine those things? So for a penetrant material to be effective, the contact angle should be smaller as possible. So it should be very smaller as possible. In fact, the contact angle for most liquid penetrant is very closer to 0 degree. It is very closer. So the second image, very closer. So small contact angle, good wetting. So large contact angle means it's poor wetting. That is what they have written there in the image itself. Small contact angle, a good wetting. Poor wetting. It means the penetrant is homogeneously dispersed onto the surface because it is floating and it is going inside. That is what it is. Good wetting is useful here. Next one I am talking about the viscosity property. The first tag statement is I have given low viscosity to permit a quick liquid flow. We understand low viscosity of water and high viscosity of oil comparatively. So the water can float easily, oil cannot float easily as because of its viscous property. Likewise, it is the internal resistance of a liquid to flow. And definition that is viscosity. It is the internal resistance of a liquid. Liquid itself, it is not permitting itself to move. So that is the internal resistance of a liquid to flow. Liquid itself resisting itself to move. A fluid that is highly viscous has a high resistance and flows slower than a low viscosity fluid. Liquids such as water that flow easily, having low viscosity than do liquids such as honey or oils, anything. It has a little effect on the ability of penetrant material to enter into the defect, but does have an effect on the speed at which the penetrant fills the defect. So it takes more time to fill. It means at one time we have to give more. That's what our understanding here. If at that time we are giving more, production rate may get reduction at the other side. But we want perfect inspection to be done, we should give the dwell time. If the viscosity is higher, the movement of that particular penetrant will become slower. So viscosity is increasing, penetrant dwell time increases. So penetrant with the less viscosity fill the crack in a lesser time. So here the penetrant dwell time increases. So here is a high viscosity, takes more time. Low viscosity, it quicks filling. See, it is at the same time of maybe 20 minutes of 20 minutes of time, it is filled at this much level only. At the same of 20 minutes of time, of 20 seconds of time, it is filled more at high viscosity because this is having a low viscous property. Next, we are going to see about a specific gravity. It is a ratio of the density of the substance to the density of distilled water at 4 degrees centigrade. Most commercial penetrants have a specific gravity of less than 1, primarily because they are made up of organic materials having low specific gravity. For this reason, water contamination sinks to a bottom of the penetrant tank. Next one, water washable penetrant thermal stability. It is the ability of water washable penetrant to resist the physical changes under the normal operating conditions. So at room temperature, there should be no change in the water. Maybe boiling at a temperature changing happens at a higher temperature, that is okay. We specifically, by our requirement, we heat it. But at the room temperature, we are doing the experiment. At those times, this thermal stability to be there. Otherwise, at fixed temperature, any temperature where the experiment is done. For that temperature, the penetrants are made. Let us assume the exercise is done at temperature of 50 or 55. That thermal stability should be there. That is a physical property of the material to be there. There should be no chemical reactions or evaporation or drying of this water washable. It should not happen at this level of inspection. Because the penetrant is made for that only. To sustain that temperature. Even it is not achieving and it is going fluctuation, it is too bad. So that stability to be there at normal operating conditions. The normal operating is nothing but room temperature or any 45-50 working conditions. 45 degrees centigrade, 50 centigrade working conditions. And then fluorescent thermal stability. The dye is used to, so we have seen about water washable, now we are seeing about the fluorescent thermal stability. The dye is used in fluorescent type penetrant loses their brightness or color when subjected to the elevated temperature. So when it is heated, it losing its physical properties such as color and brightness. If its color and brightness are not there, a visual inspection cannot be done through our normal eyes. So we need red color, we need contrast, we need a fluorescent green. If those things are not happen to the penetrant, we are seeing the properties of penetrant property. So if this color changes from red color to other color, contrastness also goes out. If the contrast is going outside, it is not useful. Because dye penetrant inspection basic principle is a contrast method. White color developer, penetrant liquid red color, it comes out, absorbs, and we are looking over there. The color is going due to thermal insufficient good thermal stability. Property is spoiling nature of visibility. So this loss is termed as heat fade. Due to heat, it is fading out its color and brightness. Aerospace material specifications AMS 2644 specifies the maximum allowable brightness loss as a function of penetrant sensitivity. Brightness is lost. Thermal stability is an important consideration during hot air drying. So, hot air drying means rise of temperature. During rise of temperature, it should not vanish. Color should not or brightness should not go. After drying only, we are going to go and inspect. Before or after developer is applied. So it may happen before or after, but the color and brightness should not change on the penetrant due to increasing of temperature. It should be stable. Next we come to the volatility. See, volatility is characterized by a vapor pressure or boiling point of a liquid. It is associated with a vaporization rate of liquids and it is desirable for a penetrant material to have low volatility or maybe you can tell high boiling point. So we see when a temperature is received on liquid to some boiling point of water, it is going to vaporize. I am using a high volatile material. See how high volatile results in loss of penetrant in open tanks. Let us assume I am using a tank and I have filled the penetrant here which is having a property of high volatile. I have filled here. The temperature is increased. At this point, due to its high volatile nature, it is going to evaporate now. So it is evaporated. It is evaporated now. So only tank will be there. So what happens? In case, let us assume in a liquid, in a crack, I have filled the penetrant inside. The penetrant having high volatile property. So this penetrant having high volatile property, and it is now the sample is subjected to the high temperature. When it is subjected to the high temperature, obviously due to its high volatile property, it is going to evaporate. It is evaporated. It means there is no penetrant. But you see, I have applied here the developer. Already developer is applied. What happens? Penetrant is not there. Penetrant is already evaporated. But we are looking for the color here. We are waiting. But already it is evaporated. We are looking for this color to show. But we don't know due to its high volatility it is evaporated. So that all should be considered. The high volatile material will dry on the part. See, it's dry on the part. It's drying on the part during a penetrant dwell time. After dwelling time, we are giving dwell time. Leaving the film that is difficult to remove. So we are not possible to take out also, or doing the drying operation needs slightly is giving some film, light film like a strain. A small film is giving there. So it is also difficult to remove because it's sticking over the sample. So that considerations are to be done. Volatility, the condition it means we should have less volatile. That is good. Volatility is good. These are good things. Volatile property. Flash point. We already discussed this to be greater than 95 degrees because hotter conditions it should sustain. It should not accident should not happen, should not flame. Flash point is a temperature to which a sufficient flammable vapor is given off a liquid to form an explosive mixture in air over the liquid. The flash point does not affect the performance of a penetrant. It's not going to affect the performance, but it is going to make the actions flammable conditions. High flash points are desirable to reduce the hazard of the fire. See, creating fire, therefore, our working environment will be around 50 degrees centigrade. So, around I am taking the double the rate, 95 degrees centigrade. We are going to normal hot environments of sun, maybe like Middle East. So there are nearly we are reaching 50 to 52 degrees centigrades. Removability. This term describes two conflict requirements. Maybe stickiness, maybe removableness. We see. First one, out of these two, the first one, the ability to be removed from the surface, leaving a little or no residual background. Residual means is staying back. There should be no residual should be stayed back there. In such a way, it should be easily removed, like water washable or solvent, anything. It should come out. It should does not have the staining power. It should not sticking power should not be there for the penetrant. Penetrant applied, developer, all that are okay. But when it is removing, it should come easily. Absorbed by the developer is different. Removable is different. So for first requirement, for this requirement, the penetrant must be maintain the dye in the solutions even when in the form of thin films on the surface of the part and without its more volatile component that have been lost during the dwell time. If in case the second one, this is first and second. On second one, resistance to being removed from the discontinuities. So now the first one is to be removed. See, first one is to be removed. Second one is resistance to being removed. To be removed easily should have resistance to be removed, because if all it is going out, then which one will be the resistance? The material which is in the penetrant itself is going out, means which one we are going to inspect through which penetrant we are going to inspect. So something it should be stickiness to be there. For second requirement, that is this one, the resistance. The penetrant in discontinuity is resisting the removal process. So here we are removal. It have some resistance for the removal. So now we are entering into the developer. So up to now we have seen about the penetrance and its properties. Now a little bit I am getting into the developers. Out of procedures, the procedure is nothing but we have on the sample we have applied penetrance, and we have cleaned this penetrant, and we have done the penetrance, and later we have applied the developer here. After a dwell time, this penetrant will be absorbed here. That we are going to verify. We have seen the penetrant. This one we have seen the properties of a flame, 95 degree, and those things. Now we want to see about what are the developers are there. So this is how we want to look at developers. The remaining part of the subjects, we'll see you in the next session. Thank you.